It's very important to the process of understanding Google Cloud and passing the certification exam that you go through the question and attempt answering it yourself first. So pause the video, work through the question. We'll catch up in just a little while and I'll show you how I do it. This project scenario is based on the EHR case study. Anonymous users from all over the world access a public health information website hosted in an on-premises EHR data center. The servers that host this website are older and users are complaining about sluggish response times. There has also been a recent increase of distributed denial of service attacks towards the website. The attacks always come from the same IP address ranges. EHR management has identified the public health information website as an easy, low-risk application to migrate to Google Cloud. You need to improve access latency and provide a security solution that will prevent the denial of service traffic from entering your virtual private cloud or your VPC network. What should you do? So I've identified a few key points that we will discuss a little more to arrive at a good solution. Now, in the requirement analysis, the key part of this is that users are complaining about sluggish response times. So the user experience has become slightly bad. And when the web application is slow, these are some of the potential problems that we have to look at. One, of course, is that the application itself might be badly written, that it is written in a non-performant way. That has not been highlighted in this case study, so we assume that is not a problem. The other issues might be with the physical hardware and the infrastructure that you've put up, right? So, for example, the distance from the server where the user is sitting could be very long, right? Could be very large. It's as if, if you were expecting somebody to come home and that person lives way far away, it is going to take longer for that person to come rather than somebody who is nearby. The other problems could be that the server capacity itself could be very low, right? So they might be using fewer CPUs, they might be using less RAM. In the example of the person coming to your place, it could be that the person is trying to come on a bicycle instead of coming in a car, right? So when you use lower power machines, you obviously are not going to get that much throughput. There could be a problem of low bandwidth. If there is only a narrow network pipe that is available, it means that a lot of traffic cannot come through, right? So you want to have a lot of bandwidth to allow multiple users to access the systems and to be able to respond to it also. Finally, apart from the infrastructure, it could be a problem with the data on the network. The network might have, or the systems might be receiving a lot of unnecessary, malicious, illegitimate traffic that is slowing down the legitimate traffic, right? So these are all concerns that we will have to look at in arriving at a good solution. Now we've got some additional points also in the requirements given to us. A recent increase of distributed denial of service attacks. So they have seen that there is a lot of illegitimate traffic coming to those servers, right? And it looks like this, even with all the others we've discussed, it looks like this might be the key problem, right? So if the bandwidth was constant and if the server capacity was constant and if you had a lot of unnecessary traffic coming in, obviously it clogs the network, it clogs the systems, and legitimate users are not able to get through as quickly, right? So I think we have a clear idea now on what we have to focus. Additionally, what this company has seen is that the attacks always come from the same IP address ranges. So they have seen a few actors somewhere in the network who are constantly becoming a problem for these servers, right? So they're continuously sending in malicious traffic or illegitimate traffic or unnecessary traffic, and blocking them would be a good first step in reducing the overall amount of traffic that is arriving at the servers. Now, we need to improve access latency. As I said, if we just block these malicious IPs, we are probably going to drop a lot of the traffic and we will have more bandwidth, more capacity available to the legitimate users. Provide a security solution that will prevent the denial of service traffic. So whatever solution that we choose has to detect and stop these DDoS attacks. So that is a primary requirement that is coming out of this project scenario. All right. So now to answer these questions, let's first understand what exactly is the Google network and how it serves traffic that is coming from the end users. So as you know, Google Cloud has this physical network with multiple regions across the world, and all of them connected through terrestrial or submarine cables, right? And traffic, apart from going over the public internet, once it arrives within the Google network, then it goes only on this network, which makes it very fast. But before it arrives at some of these key Google infrastructure points, it has to obviously traverse the public internet in many cases. When you're a consumer user, right, a general user, typically goes to the public network over the ISPs that you have a service with before coming into the Google network. So if there was a user sitting in an office or at home, and that end user is trying to connect to a web application on Google Cloud, it doesn't directly go to a data center. Instead, what happens is it goes into an intermediate place called a point of presence. And there are many points of presence across the world that have been set up by Google. And from there, it goes into the data center. And within the data center itself is the machine or the machines on which you have hosted your application, right? So there's a series of physical points that the data goes through before arriving at your final destination, which is where the application is running. Now that was the physical view of it, right? But we also need to look at it from a logical view, right? As if it was a software layer that is connected across the world. So if you look at the whole world and if you lay over it a logical network, right? So in the first case, what I showed you was a physical network where data is going from point to point. But some of those places also share a software layer that spreads across the world, right? And that let's abstract in this form. So we've got across the world a logical network, a software layer that is working on top of all the hardware that is already been set up by Google. So when a user sends data, right, any kind of application request, or they try to log in, it first hits this logical network also at some layer. Yeah? So even as it enters the Google network, even though there's a physical point to it, it also is in that physical network is embedded also a software layer that is spanning the entire world. So a data packet that arrives from any of these enters the physical system and therefore also the software layer. And we can think of this software layer, this software thing, as multiple concentric circles. Now, I don't know all the concentric circles or all the parts of this network. So I'm just looking at a couple of things that are relevant to us right now. Now, at the very core is going to be the virtual machines, which is going to be part of a VPC that you set up, a virtual private cloud that you set up, right? And remember that this VPC is not in one region, it is not in one zone, it is not in one data center, but it spans the entire world, right? So all the data regions that Google has are connected by every VPC that you set up, right? The default VPC that you set up has a allocation of IP addresses in every single region across the world, right? Which is why you need to think of it as a software abstraction rather than as a physical abstraction, because VPC is spread across the world. And within that are the physical VMs, and those VMs will be in a particular zone within a region. But before the traffic reaches your virtual machines, it has to go through the layers before that. And at the very front of this is what is called the Google front end, right? And in that, there are a bunch of products that reside on the Google front end. So any traffic that comes in first hits the Google front end and then is transmitted back or transmitted inwards into the virtual machines and whatever applications you have. With that understanding now, let's look at each of the options. Okay, the first option says deploy an external HTTPS load balancer, configure VPC firewall rules, and move the applications onto Compute Engine virtual machines. All right. So for this, let's first try to understand how a HTTPS load balancer works. When there are multiple users who are trying to use an application that is on a server, there could be a problem that there is excess demand, right? And when there is a lot of demand, the server itself is not able to serve that entire demand. So what is a preferable way of doing this? We split the load onto multiple servers. So instead of all users being served by one machine, we say, okay, some people go to that machine, some other people go here, right? Some of the requests, let's take it to another machine, and we balance the load across these so that one is not overused and also one is not underused, right? So the work of balancing the load that comes in is done by the load balancer, and in whatever way, using techniques that different load balancers might be using different techniques. One might just say, just give the first request to the first one, second to the second one, third one to the third one. Just go in sequence all over it, all the time. Others might be based on the URL that comes in. It might be based on the existing load that is there on the server, and say give to the ones that is less loaded. So whichever mechanism that the load balancer uses, it is trying to distribute the effort in responding to these user demand in an equal way across these machines. Now let's look at how the HTTPS or these load balancers work across the world, right? So in this particular case, we have sample or example data centers that are spread in a few regions in America, right? And when there are users who are trying to access applications within these data centers, one of the things could be that all of them be sent to one particular data center, right? And that doesn't make sense, because you're going to load one particular data center, and that first one, it will not be efficient. And the second thing, in terms of latency, you don't want users in North America, all of them accessing a data center in South America, because there is increased latency because the traffic, the data has to travel from North America to South America and all the way back, right? Which is many kilometers or miles, and that is not efficient. Ideally, we want to send it to wherever is or whichever data center is closest to where the user is right now. But the problem becomes, how do you identify where is this user and which is the one to send to, right? In this particular case, do we send this user over here, or can we send this user onto this data center or this user onto this data center? That question about which is the closest one cannot be handled at this level, right? It's too close to do that. So what you can imagine is, again, an abstract layer across the world, called the Google frontend in this case. And there are load balancers sitting on this logical layer. If there are users spread across the world, it first hits the load balancer or the point of presence that is closest to where the user is, right? So instead of routing these requests to any load balancer or any data center across the world, take it to the place that is closest. So when you send a request, or when you try to choose a YouTube app, or you click on email within your mobile phone, it goes via your ISP to the closest point of presence, right? And in that point of presence would be the Google front end with the load balancers and all that, which is able to make the decision about which is the closest data center to that. So somebody coming from somewhere close to North America is going to get their traffic routed to the North America data center. Somebody who's coming from South America is going to get their data routed to the South American data center. In between two requests in North America itself, again, if it's something closer to the West Coast, it will go here. If it's something closer to the East Coast, it will go here, right? So this idea of load balancing is a feature that is globally available, and it is part of the Google front end. Now, what are the plus points and the minus points with this particular solution there? So deploying a load balancer will be good because it can help reduce the latency by routing these user requests to whatever is the closest data center, right? So if you want to reduce latency, one of the things you would be doing is to get the user as close as possible to a data center, right? And given that Google Cloud today has 26 data centers across the world, you don't want a user in North America routed to a data center in, say, Singapore or India, right? You want it as close to them as possible, right? At the end, irrespective of all this cables, even if they were all fiber, a fiber network, you still are limited by the speed of light, right? And you can't go faster than that. So the closer you are, the faster is going to be your response time. Now, the load balancer has some built-in DDoS protection, but it does not have a whole lot, right? So there is some value in putting a load balancer as suggested in this option. One of the things the load balancer cannot do is to specify a denied list from a list of IP addresses. So you can't put in a few IP addresses and say, if there are requests coming from this IP address, drop that traffic, right? Don't allow that to come in. You can't do that on a load balancer. So that doesn't work well. Finally, with respect to configuring firewall rules, right? The firewall rules are configured within the VPC itself. Now, if that malicious traffic or the illegitimate traffic has entered the VPC, it's already too late for us, right? Even if it has not entered the virtual machine itself, the fact that it's come into the VPC is not acceptable, right? Ideally, we want it to be dropped even before it enters your own virtual private cloud. So, for these two reasons, we are going to eliminate option A. So, the load balancer, though it's good, not complete. And of course, too late if the traffic is already within the virtual private cloud. So option A is out. Let's look at option C now. Option C says containerize the application and move it into Google Kubernetes engine and create a GKE service to expose the pods within the cluster and set up a GKE network policy. Now this one says to create a GKE service to expose the pods within the cluster. So if you drew out this diagram, right, it is basically saying set up these applications, put it in a pod, and you expose that within the cluster using a cluster IP. But the problem with this is that only other applications within this cluster will be able to access that service, whereas a user that is coming from outside is not going to be able to access service, right? So this solution is not going to be useful for us either. But to just look at the details on that, as I said, exposing the pod servers within the cluster, it does not open it to outside traffic, and the GKE network policy in this case is only going to work on internal traffic. And even if there is additional security that we do apply within the GKE cluster itself, it still again has a problem that the data has already entered the VPC, right? And that is something we do not want. We want to eliminate the traffic. We want to ensure that the traffic does not come into the VPC at all, right? So for those reasons, we are going to eliminate option C. Option D recommends containerize the application and move it into Google Kubernetes engine. Create an internal load balancer to expose the pods outside the cluster. And configure identity-aware proxy or IAP for access. Now, in option C, we covered these two, and even though in this case it says outside the cluster, it still does not serve the purpose, right? We saw that for multiple reasons that would not work. Let's still look at IAP, identity-aware proxy, and see what this does. Now, when you have multiple applications that are hosted by, say, a company and enterprise, a user that is coming in will have access to some of them, but not all of them, right? So in this case, among these web applications, this person has access to web application 1 and 3, but not to 2 and 4. Now, how do you enforce this? One way of doing this is to have a username password approach that is different for each of them, right? So the username password that you set for this should ideally be different from the one you set for this, should be different from the one that you set for the others also. So in each case, by ensuring that this particular person has different passwords in each application or different logins and credentials, or not having some of these login and credentials, you are able to say or you're able to give access to these different applications. Now, obviously, this is a problem because we don't want to be recreating the whole idea of user and login and identity and access management individually for each of these applications. So identity-aware proxy is able to provide identity management, right? Authentication and authorization for all applications based on multiple factors. So there is within Google Cloud an implementation of a model called zero security model, and I've created a separate video on the zero security model. A zero trust model on the zero trust model, where you do not trust any of the users coming in, and you constantly evaluate who they are by checking for authentication and authorizing them after that. So the identity aware proxy is a product given or provided by Google, which can sit in front of the applications that you have hosted in your enterprise or company, and which will decide whether to allow a user to access the application or not, right? So the concept of user management, right, the identity management, having username, password and all that, is deferred to another service that is centrally managed. Now, one of the key things with this obviously is that you need to have an identity, right? You have to have an identity to see if this person has the authentication and the authorization to access each of these applications. Now, that wouldn't work, right? Because in our case, we need to have anonymous users from all over the world access this website, right? Access the application. And IAP only works for users and members with an identity, right? You have to have an identity. You have to have an email address and a password and maybe even other multi-factor authentication mechanisms. So since we have to support anonymous users, the IAP approach does not work for us. And of course, with respect to the GKE approach, as we saw earlier, the internal load balancer does not work for traffic outside the VPC, right? So overall, option D is not going to work for us. Now let's look at option B. So option B says deploy an external HTTPS load balancer, configure Google Cloud Armor, and move the application onto Compute Engine virtual machines. We already saw how the HTTPS load balancer works. It has got a presence all across the world, and it is going to sit on the Google front end, right? So just to get back to where we left off in the earlier case, there is a series of concentric circles you could think of within the Google network, and one of the first points where the traffic hits is the Google front end before it gets transmitted into your virtual machines within the VPC that you have created. So to illustrate this differently, the traffic arrives here at the Google front end, and then there is a virtual private cloud that you've defined within Google Cloud entirely. Okay. The cloud load balancing happens at the Google front end. So the first point of connect would be within the Google front end, and the load balancing happens here to say if it should be sent to one particular region or another region within the virtual private cloud that you have created. What is additionally available within the Google front end itself is this product called Cloud Armor, which is able to connect to or work alongside cloud load balancing, the load balancer, and it can apply various rules for like web application firewalls to control traffic that looks like it is a DDoS traffic. It can also control traffic based on IP lists and also geo-based, depending on what the IP is and depending on the geography, depending on the location where the user or the data is coming in, it is able to apply rules and say we can either deny or grant access to the later part of this network, right? So the cloud load balancer and the Cloud Armor sits alongside within the Google front end and is able to control traffic even before it enters the VPC, right? And is able to apply this even for specific IP lists, and that is exactly what we want. So in our case, as I mentioned, because Cloud Armor and the load balancer is sitting right at the front, right, is the first point of defense within the Google network when it comes to data traffic that is coming from outside. So it is able to block traffic even before it enters. And Cloud Armor also has a capability to choose, you can set IP deny lists or allow lists to say, you know what, don't allow these particular IPs to send traffic into the VPC, right? So that is exactly what you want. Malicious volumetric traffic like DDoS attacks are now dropped at the periphery, right? So it is dropped by these products itself, and you don't have to make a decision within your virtual machine, within your application, whether you want to serve these users. So the users or the requests that are coming in are only legitimate users, and now a lot of the bandwidth is freed up because the illegitimate or the malicious traffic is dropped right at the beginning, right? And obviously you're not going to be charged for the traffic or the application, or it doesn't cost you now because otherwise you would have had to deal with all the excess unnecessary traffic. And because only legitimate traffic reaches the VMs, you're able to get higher throughput and you're able to provide much lower latency to your users, and therefore the user experience is going to be much better for this customer. Since it meets all our criteria in this case, obviously B is going to be a best answer, and that would be the one that I choose. If you find these videos useful, consider supporting me on Patreon or buy me a coffee. Also, don't forget to like, share and subscribe for more learning videos on Awesome GCP.